Chapter 4, Vector Spaces. A vector space is a non-empty set of vectors which is closed under two operations, addition and scalar multiplication. In this chapter, we'll study basic concepts of such general vector spaces and their subspaces. Section 4.1, Vector spaces and subspaces. A vector space is a non-empty set V of objects. The objects are called the vectors, on which are defined two operations called addition and multiplication by scalars. Here, a scalar means a real number, and the set should satisfy the following 10 axioms rules. For all vectors UVW in the set V, and for all scalars C and D, here for addition, it must be closed under addition and commutative and associative, and there must be a zero vector in the set such that if 0 is added, then it should remain unchanged. And for each u in the set, there must be minus u in the set such that the addition must be 0. Now here the next 5 are for scalar multiplication, and the set must be closed under scalar multiplication. And for scalar multiple, here it must be distributive in this sense for vectors and for scalars. Now if you multiply twice, more than once, the scalars, then you can multiply scalars first, or you can apply the scalar multiplication and twice, like that. And also, the scalar 1 is multiplied, then the vector should remain unchanged. These are 10 axioms the set should satisfy. Here are examples of vector spaces. Rn are the premier examples of vector spaces. You learned this one in previous chapters. Now consider Pn is a set of polynomial of degree at the most n. And if we choose two polynomials from the set, P of t and Q of t, if we add them, then again it is a polynomial of degree n, so it must be in Pn. Now for scalar multiplication, again it is a polynomial of degree n, so that again here must be in Pn. So Pn is a vector space with the usual polynomial addition and scalar multiplication. Now we consider V is the collection of all real-valued functions defined on a set D. Again, you may consider the addition of two functions from V and scalar multiplication. Then again, the result will be real-valued functions defined on the same set D. So it is closed under addition and scalar multiplication. But the addition is usual function addition, and the scalar multiplication is usual scalar multiplication. Okay, here we define subspace. A subspace of a vector space is a subset H of V that has three properties. 0 must be in the set H, and H must be closed under vector addition. The addition is inherited from the vector space V, and H also must be closed under scalar multiplication. That means for each U and for each scalar C, the CU must be in H. Okay, here we have examples of subspaces. 0, just one entry. H is chosen to be that one. Then it is subspace. The reason is, okay, now 0 is here, and if you choose two the vectors, then you can choose only 0, 0. Addition is again 0. And for any scalar, if you multiply to 0, then again it's 0. So it is closed under addition and scalar multiplication, and including 0. So it is a subspace. It has only 0, so we call it the 0 subspace. Now P is all polynomials with real coefficients defined on real line. Then P is a subspace of the space all real valued functions defined on R. Okay. Now here there is a vector space. If you collect all real valued functions defined on the whole real line, and if you consider just all polynomials, then the addition of a polynomial will be again a polynomial, and scalar multiple also will result in a polynomial. So P is closed under usual polynomial addition and scalar multiplication, so that P is a subspace. Of course, a subspace itself is a vector space. And a vector space R2 is not a subspace of R3, because R2 is not a subset of R3. That has 3 components, but this has 2 components, so that it cannot be subset. So it is not a subspace of R3. And however, if you define H is given in this way, so that is ST, 2 components, and last one is 0. In 3D, that will occupy the flat plane with z direction 0. Then this set is a subspace of R3. It has a 3 component, so it is a subset of R3. And here, if you add 2 vectors here, or scalar multiple will be again only 2 non-zeros, and always this will be 0, so that it is closed under addition and scalar multiplication, which means H is a subspace. Right? Now, determine if the given set is a subspace of Pn for an appropriate value of n. Okay. Now, AT squared, if you choose from this set 2 entries, then that will be AT squared, and for example, another number B T squared. If you add them, then it will be again here A, okay, along with some scalar, and A plus B T squared. So that will be again a form in this set, so that it is closed under addition. Also, even though you multiply any scalar C, again is another element, so that it is a subspace. How about this one? P in P3 with integer coefficients. Okay. Now P is has all integer coefficients. Once a scalar real number is multiplied, then the coefficients may not be integer, so that the result is not in the set. And that means it is not closed under scalar multiplication. Scalar means real numbers, so that it's not a subspace. Now a t squared, okay, for that one, if you choose two functions from here, then a plus t squared, and another one is now b plus t squared. If you add them, then that will be a plus b. Okay, that is a scalar. Now plus 2t squared. However, this 2t squared is not in this form. So the set is not closed under addition, so it's not a subspace. Now, for that one, we are collecting here polynomials such that at 0, the value is 0. Now, if you choose here two polynomials, p and q, from the set, then addition, p plus q, and we here try to evaluate at 0, then there will be p0 plus q0, so that this is 0, this is 0, so it is 0. Okay, it is closed under addition. And how about scalar multiplication? We try to evaluate, then that will be 0, so that again 0. And of course here now 0 is inside the set. Now we didn't check if 0 is inside the set. For that one, if we choose a equals 0, then 0 is inside, right? And now for this one, 0 is inside, and 0, every 0 is integer, so that 0 is included. But for that one, 0, even 0 is not in the set, because it can be 0. However, the result is t squared, so that this is not including 0, right? So anyway, it's not a subspace. But for this one, 0, and it is closed under addition and scalar multiplication. Okay, a subspace spanned by a set V1, V2 are chosen from a vector space. Then we want to prove that H spanned by V1, V2 is a subspace of V. Okay. Now, okay, spanned by V1, V2 means that that's the collection of all possible and C1, V1 plus C2, V2, all possible linear combinations. If we choose 0, 0, C1, C2, then must be 0. So 0 is inside. Okay, so that is okay. Now, here, and V1, if you choose two entries, then, for example, U will be C1, V1 plus C2, V2, and V can be, okay, we'll use another coefficients, so that, for example, D1, V1 plus D2, V2, if you add them, and UN, okay, now we are using W notation, so W, then that is by adding C1 plus D1, V1 plus C2 plus D2 V2. So it is the same form along with this scalar, along with this scalar. So it is a linear combination of V1, V2, which means that it is in the span of V1, V2, the same as H. Now, same now for every choice of U and every choice of C, here CU, so U is given in this way, then CU will be C1 V1 plus C2 V2, right? Again, this is a linear combination of V1, V2. That means is in H. So we checked 0 is inside the set H, and H is closed under addition and scalar multiplication. And for these three the requirements, we may try to use linear combination, so that for any choice of U and V, U and V inside of H, here the requirement is for being a subspace is now C U plus D V must be again inside of the H. So it is closed under linear combination. For this example, from the beginning, the H is collection of linear combinations, so that it must be closed under linear combination, right? Okay. If V1 to Vp are in a vector space V, then span is a subspace of V. It should be, because span itself is collection of linear combinations, and subspace requires being closed under linear combinations. So quite naturally, span is a subspace of a vector space. H is given in this way, show that H is a subspace of R4. It has 4 components, so that it's a subset. From the beginning, we can say that it is a subset of R4. Now, every entry, if we choose here a vector inside of H, then okay, it's this form. It can be written in this way along with A. Okay, now direction for the first one is 1, and second one -1, third one 1, final is 0, and along with another scalar B. That is now first component -3, second one 1, third one there's no B, and final one there's 1. So it looks like each entry, each element in H is a linear combination of here these 2 vectors, that one and that one. So H is a collection of linear combination of these 2 vectors. So we can write here H is now span and of these 2 vectors. Let's say that's V1 and V2. Here, this one is V1 and that is V2, right? So H must be a subspace. Spanned set is a subspace. H and K are a subspace of V. Define the sum of H and K in this way. So H plus K is now a set. It's collection of U and V, U plus V. U is from H, V is from K. So we want to prove the that set is a subspace. Okay, of course, these two are subspace of V. The addition must be subset of V. First of all, we know that, and we have to show that it is closed under linear combinations. So we choose a vector, for example, P, and another vector Q from H plus K. Then P may be written as here C1, okay, so that, okay, we are using, so one from H and the other one from K, so that we may write down in this way. There is U1 and plus V1. Now Q must be, that is U2 plus V2. Of course, that is from H, that is from K. Right? Now, we consider their linear combination, CP plus DQ, then C, U1 plus V1 plus D, U2 plus V2. Okay, we rearrange these terms. Now, that is here C U1 plus D U2. We write down this one, that one first, and then now C V1 plus now D V2, right? Okay. Now U1, U2 are in H and their linear combination. V1, V2 are in K and their linear combination. Now, from the beginning, we assumed that H and K are subspaces, which means that these subspaces are closed under linear combinations. So this linear combination must be in H. That linear combination must be in K. Here, U1, U2 are in H, V1, V2 are in K, so their combinations must be in their spaces, right? So that means that after choosing arbitrary two vectors, their linear combination is again inside here H plus K. Right? So H plus K is a subspace. Okay, we reach at the true or false problems. Okay. A vector is an arrow in the three-dimensional space. Is it true? Is ridiculous. Once a vector is in three-dimensional space, we may visualize by using arrow, but a vector is not an arrow. So it is false. A subspace is also a vector space. It is quite true. And R2 is a subset of R3. That is false. It has three components, but R2 has two components, so that it cannot be a subset. So that from the beginning, we don't have to worry about the cluster under linear combinations of entries. Finally, a subset H of a vector space V is a subspace of V if the following conditions are satisfied. Okay, so here now, the conditions are basically subset. First of all, it must be subset, and 0 of the vector space is in H, and now UV and U plus V are in H. So it looks like addition is closed there. And C is a scalar and CU is inside of H. So scalar multiplication is also, it is closed on the scalar multiplication. Now, along with this statement, is it true? Looks like true. However, it is false. Why is it false? Everything is okay, except here, U, V, and U plus V are in H. This is for some specific U, V, and U plus V, it is in H. However, it is not saying that for arbitrary choices of U and V, the addition is inside of H. So when you are checking if a subset is a subspace, you have to check it with arbitrary choices. So also, this 3, C is a scalar, and CU is in H. So here, C is a specific one, and U is also a specific one, such that CU is in H. It's not enough. You have to choose arbitrary U and arbitrary C, a scalar, so that the scalar multiplication must be in H. With those requirements, the subset H can be a subspace of the vector space V. Okay? That's the end of the section. Thank you.